Hello and welcome to this video on deep neural networks from Society of Artificial Intelligence or SOAI. I am Ritik and these slides are created by my colleague Mansi. So let's begin this video from the introduction to deep neural networks. Let's see the six jars. Here, the data has the real inputs. The task is that of a binary classification, multi-class classification, and regression. We will be discussing this term later in the video in detail. The model is non-linear. The loss function has specific task defined for it. The learning algorithm will be gradient descent with back propagation, and the evaluation criteria is accuracy and RMSE. So, what kind of data and tasks have DNN been used for? One common example is digit classification using the MNIST dataset. This is a very popular dataset. Here, task is from a given image, we have to identify one of the 10 digits that it belongs to from 1 to 9. So, how can we represent MNIST images as a vector? MNIST images are vectorized using the pixel value of each cell. So, matrix having pixel value will be of the size 28 by 28 as MNIST images are of that of a 28 by 28 pixels. This figure represents the 0 using pixel value for each cell as you can see here. Now, here each pixel can range from 0 to 255. So, standardized pixel value by we standardize the pixel value by dividing it with 255 and we get the values ranging from 0 to 1. We can see here. Now, we will flatten the matrix to convert it into a vector of 784, which is 28 by 28. Similarly, we can convert all the images into vectors. Now, our task is from this given inputs, we have to predict the class label from 0 to 9. So, it is called as a multi-class classification as we have here 10 classes from 0 to 9 where all the digit can be any of these 10 digits. Now, data along with the labels. As you can see here, the vectorized form for all the class labels 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the one hot representation of it. Now, another example would be Indian liver patient classification problem. There are only two possible outcomes. Hence, it's a binary classification task. As we can see here, the value is returned is either 0 or 1. An example for a regression would be housing price prediction, where instead of predicting a discrete output, the prediction is a real number of continuous values, that is decimal fraction, etc. As you can see here, the value of house increases with a certain amount as the number of rooms increases, and if the house is old its value decreases a bit, and if the crime rate near the house is more then its value also decreases a bit. So that is how, and here we are using regression because the values is actually continuous, so here we are using regression. Now, how to build a complex function using deep neural networks or DNNs? Consider the previous used example of mobile phone, like or dislike predictor with variable screen size and cost. It has a complex decision boundary as shown here. As we had seen in the last video, it was supposed to be a circular like decision boundary. So, with the single sigmoid function, it is impossible to obtain this shape. We have discussed this earlier. Regardless of how we vary the parameters w and b, as the sigmoid neuron can only produce a shape ranging from a S shape to flat. So, the formula is y is equal to 1 divided by 1 plus e to the power minus of w1 x1 plus w2 x2 plus b, where w1 and w2 are the weights for inputs x1 and x2 and b is the threshold. So the sigmoid decision boundary can range from S shape to flat based on w and b models. We have discussed this in our earlier videos as well. Now, different outputs with the help of sigmoid function. Here we can see the sigmoid function is unsuitable for modeling, as we have also discussed this one also earlier, that see here it is not able to draw that circular decision boundary that we were expecting. So, deep neural networks for the same mobile phone, this is the graph for our deep neural network for the mobile phone like or dislike predictor. So, for the model that was shown in the previous slide, let's understand the terminology a bit. Here, the first neuron h1 is a function of x1 or x2, and h1 is equal to 1 divided by 1 upon 1 plus e to the power w1 x1 plus w11 x1 plus w12 x2 plus b1. Here w11 and w12 are the weights of x1 and x2 corresponding to the first neuron h1. So this one is the first neuron H1, and W11 and W12 are the weights corresponding to the X1 and X2 with the first neuron. Similarly, H2 is equal to F2 of X1 and X2, where H2 is defined in a similar way, which is 1 upon 1 plus e to the power W13 times x1 plus w14 times x2 plus b2. Here w13 and w14 are the weights of x1 and x2 corresponding to the second neuron h2, and b12 is the corresponding binds. Now, the output neuron is defined as 1 upon 1 plus e to the power minus of w21 into 1 upon this sigmoid this value plus w2 plus b3. Here, the w21 and w22 are the weights of h1 and h2 corresponding to the output neuron y cap, and b21 is corresponding bias. From this configuration, we have 9 parameters w11, w12 up till w22, and then b1, b2, and b3, which allows for a much more complex decision boundary than a single sigmoid with a sigmoid neuron with 3 parameters can. The output of a deep neural network would look something like this. The deep neural network decision boundary more complex than a single sigmoid neuron, as we can see this here clearly. We can see that this simple neural network already allows for a much better decision boundary than a single sigmoid neuron. The next step would be figuring out how to choose the best configuration of DNN for our task, and which is also called as hyperparameter tuning. So let's look at this DNN model in a more generic way. So this is a structure for a neuron. So you can see activation function, pre-activation function, weights corresponding to the inputs, and our activated output. So let's look at a deep neural network here. So here I refers to the layer being referenced. Pre-activation function is summation of input times waste plus bias, and the activation function is defined as 1 upon 1 plus e to the power minus ai times a. The structure of the neuron. The activation function is the sigmoid function. The construction of a neural network is a simple stacking of these neurons in layers, one on the top of the another. The outputs of one layer of the neurons become the input for the next layer. The cycle of pre-activation and activation repeats itself from the input layer till we have reached the output layer and obtained the desired function. Now, let's understand the structure of the DNN. Here is the structure of the DNN with the input layer, this one being the input layer, this one being the hidden layer, and this one is the output layer. So let's break down the term used in the structure of the DNN. So the format of W is W layer number, next layer neuron, and the current layer input or neuron. So the W213 term here refers to the weight corresponding to the third input on the first neuron of the second hidden layer. So for each layer I, where 0 is less than or equal to I is less than or equal to capital I, pre-activation function AI is wi h of I minus 1 of xi plus b1. Here, the activation function hi of x is g of aix, where g is called the activation function. The activation at the output layer L is a function h of L or O of AL, where O is also called the output activation function. Now, consider this structure of a DNN drawn in the previous slide. Here, the pre-activation output of the first layer A1, A2, and A3, A1, A1, A11, A12, and A13 are calculated using simple matrix multiplication as shown. So, here the pre-activation values are as follows. These values are just the individual rows of the dot product between W1 and X plus the bias vector. Thus, W1 times X is A1 is given by A11, the matrix A11, A12, and A13. The activation values are as follows. Hi is G of AI. They are simply the result on applying the activation function. In this case, we are using sigmoid function on the pre-activated values. H11 is equal to 1 upon 1 plus e to the power minus A11. H12 is equal to 1 upon 1 plus e to the power A12. And H13 is equal to 1 upon e to the power minus A13. Previous slides, we have calculated the activation and the pre-activation function for our DNN. So let's recap it. AI, which is pre-activation function, is Wi times x of I minus 1 plus pi, and hi is sigmoid of AI. So here is a quick sample for it. The figure represents the pre-activation function and the activation function of each layer. HL is equal to y cap, which is the output function. So here it is possible to write the output function y cap completely in the terms of x, as y cap is function of x, which is O of W3 times G of W2 into G of W1 x1 plus B1 plus B2 plus B3. Here we can see that y cap, we can break it as O of A3, which we can say as W3 times H of 2 plus B3, which in turn we can say it as W A2, with this function being represented as A2, and W2 times G of W1 x1 plus B1 being represented as H1. Here, y cap belongs to R and K is the number of output units. So, deciding the output layer, the output activation function is chosen depending on the task at the hand. For example, it can be a softmax or linear or ReLU. So, consider the following multi-class classification problem where we have to classify a fruit as an apple, banana, orange, or grape. So, at the last layer, we have to compute A3 is equal to W3 times H2 plus B2. We need to apply a function to yi cap equal to O of A3 such that the fourth outputs form a probability distribution. The output activation function has to be chosen such that the output is probability. Let's assume A3 as 3, 4, 10, and 3. To convert it into probability distribution, let's take each entry and divide by the sum of all the entries to get a probability distribution. So, doing so, we get these values, which adds up to 1, which they have to be as it is a probability distribution. So, however, this will not work if any of the entries are negative. Let's see. If we have in our entries like 7, negative 2, 4, and 1, then the output corresponding to the negative 2 value comes out to be minus zero point 0.2. And we all know that the probability cannot be negative, so the an output less than 0 is not acceptable. So now let us consider the softmax function, which is defined as e to the power zi divided by summation of j equal to 1 to k e to the power z of j for I equal to 1 to k. So here in this particular softmax function, Output of e to the power x is always positive, irrespective of input. Thus, this property is important to counter the negative values of shortcoming that we observed in the previous example. Now, let us illustrate this softmax function as the last layer of our neural network. Here, A is A1, A2, A3 and A4. By applying the softmax function, we get softmax of A as softmax function applied each to A1, A2, A3 and A4 respectively. Here, raising the numerators to e to the power x ensures that all are positive. The denominator is just the sum of all the values raised to e to the power x. The softmax function softmax of a of I is the ith element of the softmax output. So, for our multi-class fruit classifier, the equations are as follows. For hidden layer 1, it is A1, for hidden layer 2, it is A2, and for the output layer, it is defined as A3, where the output for the first hidden layer is H1, it is H2 for the second hidden layer, and the output layer is Y cap or the output equal to softmax of the A3. Now, let us consider the dataset in 2D and 3D. Here we can see that for 2D and 3D datasets, we can see that whether the data is linearly separable or not. However, in real life scenarios, datasets often approach 1,000 to 10,000 dimension. So, there is no way to visualize the data to a certain non-linearity. In order to choose the best configuration for our neural network, we need to try out different combinations and select the one with the lowest loss. Here are some examples. Here are some samples configuration for the corresponding losses. From the figure, it is evident that fourth yields the lowest loss. This process of tuning the DNN, that is, the number of layers, the number of neurons in each layer, learning rate, the batch size, etc., are together called as the hyperparameter tuning. In normal cases, the number of neurons in the output layer would be equal to the number of classes. However, a shortcut in a case of a binary classification would be use only one output neuron that uses a sigmoid function. Here is a diagrammatical representation of the configuration. So the output y cap is equal to p of y equal to 1. Therefore, we can obtain p of y equal to 0 as 1 minus the probability. Consider the following values for the variables b as zero point 0.5 and zero point 0.3 and y being 1. So the w1 matrix is as given below, w2 is as this, and x is defined as zero point 0.3, zero point 0.5, minus zero point 0.4 and zero point 0.3. The output values are as follows, with zero point 0.8 being the maximum and 0.52 being the minimum. And in this case y equal to 1, the true distribution is 0 and 1. Thus the predicted distribution for y cap turns out to be 0.2793 and 0.7207. The cross entropy loss is defined as L of theta equal to y of minus log of y cap plus 1 minus log of y cap. In this case, since y is equal to 1, the L of theta turns out to be 0.327. So here is an illustration of a simple multi-class classification neuron. Here three class, basically we are classifying into the three classes. Consider the following values for the parameters, b being 0 and w1 and w2 being the matrices. So consider a case where x is equal to minus zero point 0.6, minus 0.6, 0.2 and zero point 0.3 and true class y equal to 0, 1, 0. The output values are as follows. A1 being w1 b1 plus b1 times b plus b1 and h1 being sigmoid of a1 and a2 being the w2 times h1 plus b2. The cross entropy loss is defined as the summation of I equal to 1 to k yi log of yi cap, which turns out to be 1.2729 in this particular case. The weights can be obtained from the learning algorithm. Consider this following neural network. So the learning algorithm corresponding to it as follows. We will be first initializing the weights w11 to w313 and b1 b2 b3 the thresholds value randomly. Then we will be iterating over the data in order to compute the ycap or the output. Then we will compute L or loss function in terms with parameters weight and threshold parameter with cross entropy loss function. Next, we will be changing the value of w11 as w11 minus eta times the gradient of triple one or w111, and we will be doing the same with all the weights. And the similar thing, we will be changing the value of bi as bi plus eta times the gradient of bi. Then we will have be using the libraries such as PyTorch, which is developed by Facebook, and TensorFlow, which is developed by Google, and have the functions to compute the del L by del W and del L by del B till till the condition is satisfied. Then we will be iterating, then we will be reaching around the epochs we wanted, say 1,000 passes per epochs, and continue till the loss function value is less than the epsilon, which will be some defined value. It is generally very close, we define values which is close to 0, so that we will get a better accuracy. So, how do we check the performance for a DNN? Let's understand this by an example. Consider the previous Indian liver patient diagnosis task. Here, the accuracy is about 2 by 4, which is 50%. Okay. So, here, one question is, how do we resolve a probability distribution like 0.45 and 0.55 to a specific binary output? See, this both are very close to say zero point 0.5, so we cannot for sure say it as it is miss or yes or no. So it is done by picking the class that corresponding to the highest probability. In the above case it is 1. So for a multi-class classification, the concept remains the same. The label is selected based on the highest value in the probability distribution. The predicted label corresponding to the index value of the highest value in the distribution in the probability distribution is argmax. So this figure represents the example of a multi-class classification. As you can see here, we have 0, 1, 3 and 5. So for this, in addition to accuracy, we can also calculate per class accuracy. In this case, the accuracy for the class 1 is 50% and that for class 5 is 100%, as y predicted, y output and y predicted is equal. This allows us to analyze where the model is performing poorly and enable us to take steps to improve the accuracy for lagging classes, such as adding more images or adding more or training our data on a particular images, so that it accuracy increases. So for the summary, let's once again revisit the 6-star models for our DNNs, where our data were real inputs where X belongs to R. The task was binary classification, multi-class classification, as well as regression. The model we used were DNN with in order to deal with the complex decision boundaries. Loss function was defined as cross entropy loss, which is defined by this our function. The learning algorithm was gradient descent, and in which we used the back propagation, and the evaluation criteria was defined by both accuracy and per class accuracy. As you can see, as before, the accuracy is the number of correct prediction upon total number of predictions, and the per class accuracy is defined as number of correct prediction of a particular class divided by total number of true values for that class. As you can see in this very particular example here, if we take 3 as our class, here the output was 3 and predicted was 8, so we can say that the accuracy is around 3 by 8 or around 0.375, which is 37.5%, which is a bit low. Whereas in case of a In case of a class 5, here the class accuracy here y predicted and y output is 5. Both are equal and hence the accuracy is 100%, which is very good. So thank you for watching this video.